So actually here I told you that whenever you have a loop, say f in pi1 x comma x0, okay, then for one loop f you can always define f bar. It is kind of f inverse. Okay, so how to define that? So this is again a path and it is defined by this t equal to f of 1 minus t. So that's mean, suppose now I am going to path, not the only loop, because it is more general. Now suppose this is your x0, so this is your x1. Forget about that loop. Okay. Now suppose this is your f. F means it start from x0 and it is going and stop at x1. Okay. And then what will be f bar? That will be the same thing but with the reverse direction. That's mean it will start with x1 and then moving to this direction. Okay, so starts with x1 and ends at x0. So what is actually f dot f bar in this case? So in this case, f dot f bar means, so we have 2 points, say x0 and x1. We first go x0 to x1, right? Half time. So from 0 to half, we will move this to this one. And then again from half to 1, we will come to this to this. So this is just my path. Okay. So here in this case, this will be a loop. So anyway, now in particular, if f is a loop, say this is my f, then f dot f bar will be, now first we go to this one and then move back to this. So this is my loop, right? So this is my now f dot f bar. Now what we need to prove that? We need to prove that f dot f bar is homotopic to that constant part ex0. Ex0 means it is not moving anywhere. So it is just a constant part. So ex0 x, sorry, t means it is always x0 for all t belongs to 0 1. So how to define such path homotopy? So what we will do? So actually the main idea is we first, so what is this path f dot f bar? So when we have 0 to half, it will go stop here at half, right? Again half to 1, we will go this to this, right? Now what we will do, we will not go up to half. Okay, we will stop somewhere before half. So what we will do now, now say this one. Now what we will do, now this is something, say before half is a point, say it is some half minus a t by 2. Okay, and for some positive t. So what we will do now, we go this to this. Okay, and what we will do, so between half to t minus half minus t minus 2, during this path we will go this to this and we will stop here. So remaining t by 2 time we will stop here, we will take rest. Okay, and again similarly again we take rest another t by 2 time and then again we move back to this direction. Okay, and similarly when t increases we will move like this way. That's mean again we will go, sorry, that's mean again we will go to this direction. Okay, and we will stop here for few times and then again we come back this. And similarly now t, now if we increase the values of t, because my path is half minus t by 2, that path will be look like this one, this this, right? So it will be moving in this direction. That's mean, this means we are going to this and taking rest here, right? And then again after come back to this. So again if you take highest value of t, now this way. Now this is my path actually. So that's mean we are going to this direction, we are going here, and we are taking rest, and then we are again come back to this point. Now similarly, if your t is when it is 1, then it will be just your this identity path. Okay, so that's mean that if this one is homotopic to this identity path. Okay, so this is the main idea actually. Now I hope everyone understood this idea, right? Okay, so that's mean we have seen that. Anyway, so any problem? It is fine, right? That idea. Okay. See, you should speak. Otherwise, I do not know that you are getting or not. You have to at least say something. So you cannot keep quiet only. Okay. So that's mean what we have seen. So let X be a topological space, right? We choose a point x0 from X, right? And we take this set pi1 x comma x0, that is a collection of homotopy class of loops with base point at x0, right? And we have seen that this forms a group, right? And under the product, this one. So if G, it is just by defined by this one. And we have seen that all this product is well defined and everything, right? So this forms a group. Now from nowwards, we will call this group. So whenever we say pi1 x comma x0, that's mean we will not assuming this notation by a set, right? By this notation, we generally call the group of that all collections of the homotopy classes of loops with base point x0. Okay, so by these notations we will call the group. Now since this is a group, now this has a special name, right? So now this group is called fundamental group. Now this group is called the fundamental group of the topological space X. Okay. Now what is the next question from this? So first of all, we have seen that whenever we are defining this group, we are taking a point x0, right? So that's mean if you change this point x0, that group will change, right? And since X generally it is a topological space, it should have means actually infinitely many points because X may not be finite. Generally, most of the topological space, well-known topological space, are infinite, right? So therefore, if we change the base point x0, then how this group will change? It will be totally changed or what? What kind of group it will be? So that is a natural question, right? Now we give the answer of this question by this one. Now that is very important theorem in this sense. It says, so let x0 and x1 be 2 points in X. Okay. X has 2 points, x0 and x1. Now suppose given that there is a path in X between them. Okay. So that's mean, what does it mean? There is a path between x0 and x1. That's mean there exists a continuous function, or you can say path from h, say 0, 1 to x. You can say there exists a path this, or you can say continuous function h such that h0 equal to x0 and h1 equal to x2. Okay. Now if these 2 points connected by a path in x, then this theorem says pi1 x comma x0 is same as pi1 x comma x1. Since these two are a group, so we say that they are isomorphic. So by this notation, we generally write isomorphism. Okay, so I am using this one for isomorphism and this one for path homotopy. Okay, so that's mean if you have a topological space X, now if you choose 2 points x0 and x1, okay, and if they are connected by a path, then the fundamental group pi1 x, that is the fundamental group with base point x0, and the fundamental group with base point x1, both are same. Same means both are isomorphic. Okay, now we will prove this one. Okay. Now first of all, let that f belongs to say pi1 x comma x0, say x1 first. Okay. Now what does it mean by this one? That is that homotopy class belongs to this. That's mean f is a loop in x with base point x1, right? So this is your x0, this is your x1, and this is something f. Okay, so it is just a loop with base point x1. Okay, and now let h be a path from x0 to x1. So that's mean we have a path this x0 to x1. So that is h. Okay. So what is the end point of h? That is x1. And what is the starting point of f? That is x1, right? So therefore h dot f, that is well defined, right? Now again, if we take h bar, right? H bar means it is a path. It is the path from x1 to x0. So therefore, if we define this, so h bar, now this is also well defined. Now what does it mean by this path? That h f h bar. So that's mean this is the path. So this, then we have this direction, and then again we come back here. Okay. So that's mean it is a loop with base point x0. So then this is a loop with base point x0. In other words, we can say that that class, so h f is closure, that is belongs to pi 0, sorry, pi1 x comma x0. right? Or in other words, it is, you can write in this way, belongs to pi1 x comma x0, right? Is that fine with all of you?
Yes, sir.
Yes,
Okay.
sir.
Now, can you tell me how can we define a function? That is, we need to find a isomorphism, right? From pi1 x x1 to pi1 x x0. So how to find that isomorphism? So we can now define in this way, right? So let's say something called fh, because it is depending on h. Okay. Say pi1 x comma x1 to pi1 x comma x0. Okay. Say be a map defined by fh f in this way, or you can say in this way directly, h f h bar. Okay, right. Now first thing, what we need to check? Tell me what we need to check here.
Well defined.
Exactly. So first of all, we have to define, we have to check that it is well defined or not. Why we need to check that? Because there is a high chance that when we define this kind of function, that is not well defined. Why? Because here our elements, that is a class of elements. So it may happen that whenever we are applying some maps, it may happen that some elements of that class going somewhere and some elements of that class going some other places, right? In that case, the function will not be well defined. So we need to check that. So how to check that this function, this map is well defined? So what is the idea behind that? So how to check that if this function is well defined? Our age is fixed. Now tell me, what is the idea? Because you should know, because whenever you will solve a problem during your maybe examination, then you should know, because anyway this one will not be in exam, so there will be something similar to that. So
Like
there you have to check.
we'll have to show that if F1 like if F1 and F2 belong to the same class, then HF1 H bar and HF2 F bar also belong HF2 H bar also belong to the same class.
Right, right, good. So that's mean actually we need to show that well defined, we need to show that if say f is homotopic to g, right, then we have to show that that should imply that h f h inverse homotopic to h g h inverse, right? So that is the meaning of well definedness here, right? So this, so that's mean actually that f equal to g, that imply actually fh f equal to fh g. So this is the same meaning. Okay. Now that is actually trivial. So how to check that is trivial? So first of all, you can check that. So let f0 and f1 are homotopic, or you can say like f0 f1, that is homotopic via the homotopy ft. Okay, so that's mean you know that what is that continuous map, right? So that's mean that was the continuous function, right? Okay. Now if this f0 and f1 homotopy via the homotopy ft, now that will trivially imply actually, so h dot F0, this one is homotopic to H F1 is this. What is the homotopy now? That homotopy is also simple one. That is via homotopy H FT H closure, right? Because H is a path from x0 to x1. What is ft? For each t, ft is also a loop, right? With base point x1, and this is again a function from x1 to x0. So that's mean this is actually again a loop for each t. This is a loop from a loop with base point x0, right? And see, this is a homotopy between this function and this loop and this loop. Okay. And why this is continuous, we have seen that, right? So whenever we have this composition, so these are always continuous. We have seen that. Okay, so this is homotopy. So that means we are done. So that implies the function that fh is well defined. Okay. And also it is now easy to check that this is 1 1 and on 2. This is very simple. So again here, since it is the first time, so I can check. Okay, so first of all we can check it is a homomorphism. It is well defined first. Is homomorphism. Now again, this is also simple. So first you can take fh, say fg. Okay, now what is that? That's mean fh that f dot g. Okay, and note that whenever we are writing this and this, we are not giving any product here, right? When we are taking only that path, we generally write f that dot g. Okay, and when we write in terms of class, we just write there together only. Okay, we will not put any dot. This is just a notation. You can follow this notation. That will be good. Okay, so here we have a dot. Now by definition, this is h again dot f dot g dot h closure, right? Sorry, h bar. Now how to define? Now we know that h and h bar, they are inverse to each other, right? So therefore we can write here h f h bar h g h bar. So this is, and we just use that my associative property. So we are not writing where we are using associative and where we are using only that product, because that is now well understood. Now that's mean it is FHF FHG. Okay. Now since this is the first time, so we are just proving this. That is very simple. Now from now onward, now if you can see this proof, you can write clearly this is a homeomorphism, because that is fine, right? Of course, you have to feel that that is a homomorphism, right? Now you need to prove that f is 1 1 and on 2. Now again 1 1 is also simple. Now how to prove that? Now this is also simple. Say FHF equal to FHG. Okay, now that imply so HF bar HG bar. Now what we can do? Now we can just take the product on the east side. So we can take the product of H bar here, and we can take the product with H, and similarly in this side. So since this is a group, we can do that, right? Now that will be here by using that associative property. So these are the simple math. Now this is identity, or you can, if you want, you can just keep that, or that will be that equal to this. Right, so 1 is very simple. Now similarly, you can prove that that map is onto. So onto means, so if h that was a function from pi1 x comma x1 to pi1 x comma x0, right? Now take say g from this, so pi1 x comma x0, this one. That's mean g is a loop with base point x0, right? So we can write that imply g is a loop with base point x0. So therefore we can also do the product as well. Now what we can do? Now we can product that h bar and h with g, right? Now if we take h bar, now what is h bar? H bar is a path from x1 to x0. So its endpoint is x0. Now its starting point is x0. So it is well defined. Now the endpoint of g again x0, and we can product with h because starting point of, right, h is x0. So this is well defined, and this is a loop with base point x1. So that's mean you can say that one belongs to pi1 x comma x1. Now actually it is easy to see that this is actually the what inverse image of g. Why? Because now you can easily check that if h of this one is same as h, right? Now you can do that associative property. So you get this identity. So this is g. So therefore this is onto. Okay. So therefore if you have x is any topological space, and if you have 2 points x0 and x1 which is connected by a path, then we can say that pi1 x x1 and pi1 x x0 are isomorphic. That is, this is an isomorphism. Or you can say pi1 x x0, this is isomorphic to pi1 x x1. Okay. Now in general, actually in this algebraic topology, or when we actually work on these topological spaces, we generally take a path connected topological space. Now do you remember what is a path connected topological space? So any MTech student, can you tell me, the BTech MTech student, what is a path connected topological space? Is there any? Yes, there are. So do you know what is the definition of that path connected topological space? So do you know what is path connected? Yes or no? If you know, don't know, then I should define. There is no MTech student here. Okay. So from this we have a corollary. So let X be a path connected topological space. So what is meaning by that path connected topological space? That's mean for any 2 points say x0 and x1. So better to say x and y. X and y in X, there exists a path say H from X to Y. Okay, so that's mean any 2 points of that topological space should be connected by a path. Okay, so if X is a path connected topological space, then the fundamental group of X, that is pi1 X comma X0, okay, is, you can say, up to isomorphism is independent of choices of x0. So that's mean you can say that for any 2 points x0 x1 in X, we always have pi1 X comma x0 is isomorphic to pi1 X comma x1, right? Because X is path connected topological space. So therefore x0 and x1 are connected by a path. So therefore by the previous theorem we can say that both are isomorphic. Okay. Now since that fundamental group is independent of choice of the base point, so therefore there is no meaning of write that specific base point, right? Because when we say about the fundamental group of topological space, that will be unique, right? It is independent of x0. So thus we often write only that pi1 x as the fundamental group of X. Okay, obviously, if X is path connected. Okay, so if X is path connected, then generally we write only pi1 X. So that is my fundamental group. Okay. Now I define another important concept that is also very important, not only in the top algebraic topology, it is also important in any field. Okay, that is called simply connected topological space. Now, what is the meaning of simply connected topological space? Okay, so first of all, let X be a path connected topological space. Okay, so that's mean For the simply connectedness, so when you want to define when you say simply connected, that's mean X is trivially path connected as well. Okay, because under definition of simply connected, we need X to be a first of all path connected. So if X is not path connected, then it cannot be simply connected. Okay. So first of all, let X be a path connected topological space. Now then X is said to be simply connected if pi1 x equal to 0. Okay, so generally we write in this way, pi1 x equal to 0. That's mean the fundamental group is trivial. Fundamental group is trivial. Okay, so that's mean that fundamental group has exactly one element, and that is that constant path. Okay, so why we are writing here 0, not that constant path? Because we do not know what is the base point, right? So if you know the base point, so this is actually equivalent notation. So pi1 x equal to just write 0. We are not writing this 0. Okay, we are just write pi1 x equal to 0. So that's mean it is a trivial fundamental group, and which is equal to, which is same as pi1 say x comma say x0. Say it is base point x0. That is the meaning of it is the group generated by ex0. So this one only. Okay. Generated by the constant path that x0. Okay. Right. Now we may have another interesting theorem. It says a space X is simply connected.
Hello.
Yes.
So like we are saying the pi1 x naught is nothing but the group generated by constant path x naught. तो pi1 x naught में classes होती हैं और homotopy path और loops. तो इन इट मींस जितनी भी लूप्स बनेंगी मतलब वो सारी होमोटॉपिक होंगी एक दूसरे के. ये
Right.
एक ही क्लास है हमारे पास.
हाँ.
ओके.
For an example, suppose fundamental group of R2. तुम कोई भी लूप ले लो, वो लूप को तुम मतलब होमोटॉपिक हो जाएगा कांस्टेंट में, क्योंकि बाय द स्ट्रेट लाइन होमोटॉपी, राइट? यू कैन डिफाइन ए होमोटॉपी.
ओके सर.
So simply connected means that one only. Suppose you have Rn, or say you can R2. Now if you take any loop, that loop can be homotopic to a constant loop by the state line homotopy. Even if you take any convex set maybe in R2 or in Rn, then also you can define the state line homotopy, and you can say that any loop is homotopic to the constant loop. So therefore that is a simply connected topological space. Okay. Now this theorem says that is also very useful, but actually this is a very easy to see, but it is also useful. Now a space X is simply connected if and only if for any 2 points if and only if there is a unique homotopy class of paths connecting any 2 points. Okay, so that's mean if you have a simply connected topological space, that's mean fundamental group 0, then whenever you have choose any 2 points, and if you choose any two path connecting them, then those two paths should be homotopy. Okay, and it is also conversely. Now suppose you have any 2 points in a topological space such that whenever you are taking any path connecting them, then all the paths are homotopic. Okay, that's mean we have only unique homotopic class, and then we can show that the space is topology, that is the space is simply connected. Actually this is very easy to see. If you just see vaguely, right, it is easy to understood, right? You can easily feel that, but you have to write the proof of that one. Now what we can take, we can first take this one. So let X be a simply connected topological space. Okay, so first we assume X is simply connected. Then we prove that if we choose any 2 points and if we choose any two paths connecting them, then they are homotopic. We have to prove that. Okay. Now since X is simply connected, that's mean it is path connected, right? Now that implies X is path connected, because simply connected implies path connected. Now since X is path connected, so that's mean if you choose any 2 point, then they are connecting by a path. What we need to prove? We need to prove that those paths are unique. Okay. So let X and Y be to let X0, X1, okay, X1 be any two paths in X. Okay. And let F and G be two paths.
So you meant x0 and x1 are any 2 points, no?
Oh, sorry. Right. Any two points in X, and F0 are paths from X0 to X1. Okay. So that is F and G both are function, that is continuous function. These are paths such that F0 equal to G0 equal to X0 and F1 equal to G1 equal to X1. So that's mean this is the case actually. So this is my X0, this is my X1, and say this is my say F, and say this is my G. Okay. Now can you guess it how to prove that F and G are homotopy?
We can take f dot g bar and
Exactly. Yeah, that is done. If you take F dot G, that is the only a trick, right? So what you have, so we know that any path is that is it has that fundamental group is trivial, right? Now we have path F. So take this one, and if you take F and take say G inverse, then it will be a leaf loop with base point x0, right? But we know that any loop with base point x0 is trivial because the fundamental group is trivial. So therefore, f compose, that is f product g bar, that is identity. So therefore, f equal to g, that is f homotopic to g, right? So that is the proof is simple. So since this, so therefore f dot g bar is a loop with base point x0, right? So that imply f dot g bar that belongs to pi1 x comma x0, and we know that is 0, but here we have base point, so we can write it as ex0. That is the singleton set only. So that imply f dot g closure, sorry, g bar, that is homotopic to ex naught. Now that implies f dot g bar dot g, and that will be, that imply f homotopic to g. So we are done. Okay. Okay, now this part is done. Now we have to prove the other parts. Now other part is also simple. Now look at the statement. Now can you prove the other parts?
Yes.
So now it is given that any two paths, so any, sorry, there is a unique homotopy class of paths connecting any 2 points are unique, and you have to prove that X is simply connected. So how will you prove that?
Like we can take the special case where x0 equals x1 and then it will be trivially true.
Right. But you need to prove another thing. So do you know what?
Uh, oh, right.
You will,
That it is path connected first.
right. So because it is, see, this is given that, see the statement, there is a, forget about unique, huh? There is a homotopy class of paths connecting any 2 points, right? That's mean whenever you have 2 points, so that's mean there is a path, or you can say unique homotopy class. You can forget that one as well. That's mean there is a path connecting 2 points. So that's mean the space is path connected. So that is done. Now we have to
Wait,
prove
but
that
the class of paths connecting 2 points, can't it be an empty set?
empty set.
Like
No,
we are just saying that there is a unique homotopy class of paths connecting any 2 points, but
that's mean we are giving the existence of a path at first of all, and then we are proving that that is unique. So actually this statement is saying that there is a path connecting any two
okay,
point, and those classes are unique.
okay, okay, thank you.
Okay. Actually this is saying that if you can find a different meaning of that in terms of English, but in that case anyway, that is not the statement. The statement is actually there is a path connecting any 2 points, and if you take those collections of paths, those forms a unique homotopy class. That's all. Okay. And then what we will choose? Now we will choose the special case. As he suggested, we will take that x0 equal to x1. Right. That's when both 2 points are same. Right. That's when we are taking that loop. So connecting the same points. Now it is saying that that homotopy class is unique. Homotopy class of those paths. So therefore it is trivial. We are done. Okay. So we can write. So first of all, we given that is conversely, converse statement, this one. Now given that for any 2 points in X there is a path connecting them. So thus X is path connected. Okay. Now let X0 belongs to X. Be arbitrary. Now since the homotopy classes of paths connecting any 2 points are unique. So that's mean the homotopy class of loops with base point x0 is also unique. Right? Now since ex0 is already a loop with base point x0, and we know that all the loops are unique, so therefore those any loop with base point x0 is homotopic to ax0. So thus pi1 x comma x0, that is trivial. So we are done. Okay, the proof is very simple. Right. Now we prove another interesting thing, that is how to calculate fundamental group of product space. Now that is actually again trivial. So today I am proving only the trivial proofs only. So let x and y be to say path connected topological space. Okay, so then pi1 say x cross y is isomorphic to pi1 x product with pi1 y. Okay, so that's mean if you take any two path connected topological space, then we know that x cross y means that Cartesian product, right? So we will prove that the fundamental group of x cross y is isomorphic to that fundamental group pi1 x cross pi1 y. Okay, so you have to prove this. So first of all, note that what is that continuous function between these partition products. So that is very important. So again, I recall this part first. So for any three spaces, say x, y, z, okay, So a map f from say z to x comma y, no, not x comma y, it will be z to x cross y defined by say f of some z equal to g of z comma h of z. Now obviously f is your so if you take any point here, right, now that point will be some ordered pair, right, in x cross y. So therefore one portion will goes to x and another portion will goes to y. So therefore in this way we can always, if we have a function, we can always, it is defined by some this, right? We should have some coordinate function here, g and h. So in fact any map should be defined by this way only, right? Now then it is known that here f is continuous if and only if both g and h, or you can write in this way because that is not clear. So g will be a map from z to x and h will be map from z to y are continuous. So that is a simple result from topology. Okay. So you will use this fact here. Is that fine? You also know that this one, right? It is also the similar result in our calculus course as well. Is that fine?
Yes, sir.
Yes, sir.
Okay. Right. Now let f say I to x cross y be a loop. Be a loop. So first of all, I can write it is be defined by f of t equal to in this way. So in this case, our z is just I. So gt ht. Now let f be a loop with base point say x0 comma y0. Okay. Now tell me if if f is a loop with base point x0 y0, what can you say about g and h? Just use the definition of loop.
So G will be a loop with base point x naught and H will be a loop with base point y naught.
Right. So that is a simple observation, right? So then G is a loop with base point this, we can write if and only if G is a loop, we can say loop in X with base point x0 and H is a loop in Y with base point y0, right? This is if and only because if you have a loop in X and if you loop in Y with the base point x0 and y0, then you can define in this way, and F will be also a loop with the base point x0 and y0. Right? Fine. Now another thing is clear. That is, so let f0 t equal to g0 t comma g1 t. Oh, no. h0 t, and say f1 t equal to g1 t comma h1 t. Okay. So these two loops actually so base points x0 comma y0 in x cross y. Okay. Now say f0 and f1 be two loops. Now then again it is again trivial. So f0 is homotopic to f1 via the homotopy ft is imply that, or at least it is both way true, g0 is a homotopy with a g1 via the homotopy gt and h0 h1 via the homotopy ht. This one you can also vary. You just verify this one. That is simple, right? Because if this is homotopic to this one, then you can see that by using the definition, since each of ft is continuous, right? So therefore gt and ht will be continuous, right? And again this will be a path, and that will be a homotopy from g0 to h1, g1 and h0 to h1. Okay, so that is also simple. Now again you can define a simple type of map. Now let us define a map f from say pi1 x cross y to x0 comma y0 to pi1 x comma x0 product with pi1 y comma y0 in this way, that f of this f will be g h. Okay. Now this map is that f is well defined. Now from this you can say that f is well defined. How to show that it is well defined? We have already proved. Can you tell me why we have already proved that f is well defined?
Yeah, we have shown that like if f0 and f1 are two elements in the equivalence class f, then and
Right,
f is g comma h, then g0 and g1 will also be homotopy,
right.
and
So
h0 h1 will be
so
homotopy.
this portion actually, this right arrow, it shows that f is well defined. Okay. So this shows that f is well defined. Okay. And that reverse portion, we can take it different. Now this reverse portion, this one shows that f is 1 1, right? Because if this equal to some say g0 h0 is same as g1 h1, then you can show that f0 is same as f1. So that is, it shows that it is 1 1 as well, right? And also it is bijective, it is from the construction. If you look at this one, yeah, so this portion, oops, now this portion shows that it is onto as well, right? Because if you take any loop here, any loop in here and any loop here, then you can find a loop here as well by defining that, right? So by that green actually, which we are, oh, so this portion shows that f is onto as well. Okay, so that's mean f is well defined and f is bijective. That now only thing is show that f is a homomorphism. Now that is also simple. Now let f and say f dash t equal to g dash t h dash t b2 loops in x cross y with base point x0 comma y0. Okay, then you can see that f of f dot g, so you can write it as
Sir, it should be f of f and then f dash, right?
right. No, that is actually simple. Only just we have to write only this one. Now I am just searching how to write in this way. So by the definition, it is this. So g dot g dash comma f no, h dot h dash. Right. It is by the definition of this, and again, it is just a product of path. So it you can write it is in this way. Since it is just a component-wise product. So therefore, F is homomorphism and bijective, so F is an isomorphism. So thus we have this. So pi1 x cross y is isomorphic to pi1 x product with pi1 y. That is also simple one. Just we have to follow the way we have to prove it.
Sir, how did we write the second step? Like f of the class of f dash, that f dash is the next step.
This one,
Yes, sir.
that is just a definition. This one. Okay, so if you have f t equal to this one, f dash t equal to this one, now what is actually your f dash, f dot f dash t? That will be component wise product only. Okay, so in this way you can just write that. Because this way it is defined. Okay. So obviously we have to first define how we will do that product in the cross. In cross we generally do the product in this way. So we do the product in the first component as well in the second component. That is the standard one. Okay.
Yes, sir.
Okay. Now, okay. Now these are actually the all thing which is very trivial. And now in the next lecture, I just quickly overview from on the next lecture. So next lecture, I shall prove that the fundamental group of circle is Z. Now remember that in this during algebraic topology course, so there are actually 3-4 theorems. They are very difficult. Difficult in the sense that this is the real test of algebraic topology. So if you are not in that field, obviously most of you are just take this one as a course, right? You are not doing research on this one. So you will not find the interest on those proofs. So there will be 5 or around 4 or 5. And similarly in topology also we have seen some proofs, right? Say what are the things that Euration lemma, Euration metrization theorem. So there are few things we have proved there, though we do not, most of the students did not like that. But here also we have to prove something. Four or five theorems there will be. They are very difficult. Those are actually the test of algebraic topology. So maybe some of the students may not like it, but for a course also you should understand this. Now I am just quickly go through the idea. What is the idea behind that? That fundamental group of circle is Z. Is just a set of integers. The idea is very simple and the proof is very difficult. Now first of all, what is a circle? So we know that circle is just circle means this is just a circle, right? Circle means S1. So it is hollow. It is just a kind of loop. Now suppose we choose a point, say x0. Okay. Now how to calculate the fundamental group of this circle? Now obviously, can you give one non-trivial loop on here? Now suppose my circle,
Like
yes,
here circle is considered a subspace of R square.
right. Or
Okay.
we can write it is as say cos 2 pi t comma sin 2 pi t.
That will give us the mapping from 0, 1 to the 7.
Right. Now if we take only h1 equal to this one, right? Then we can get circle. Now see, if we take this map, say f of t equal to this one, cos 2 pi t comma sin 2 pi t. If we take this one, so that's mean at the point 0, so this is my x0, right? That's mean you can say it is 1 0, right? Now see, if you take t equal to 0, that's mean that point it is 1 0, right? Now if you increase your t, it will be going in this direction. and when t equal to 1 it will come here, right? So this is my one circular region. Now this is my f. So this f, if this is my s1, belongs to that pi 1 s1 comma the point at 1 0. Okay. Now what is your guess actually? Can you say that this f is can be trivial or it is a non-trivial? Can you make a homotopic to this identity? Can you make it? So can you give one homotopy with f to identity? Can you use straight line homotopy first of all? Yes or no?
No.
No, right? But see, if we have in R2, if we have this circle, then we can always use that straight line homotopy by this way, right? Because all of these points are in R2 only. But when we are talking about only that space is S1, we cannot contract this one to a single point, right? That's mean this is a non-trivial. So by looks like it looks like a non-trivial. Now this is one element. Now what if it moves one direction and then again one direction and again stop here? Okay. So if it rounds twice, then we will have same other function, say g t, which is cos 4 pi t comma sine 4 pi t. We have this one g. Now can you say that f and g are homotopy? So f and g both are loops. F is this one, g is this one. Now what is your guess? So can you see that f and g are homotopic or not? So what do you feel? Yes or no?
Actually, we can write that function g as if compose some function phi, and phi is no.
Phi, phi is representation of that one. No, that will not work.
No.
So actually that will be a different thing. Okay. So that's mean different thing. So similarly, if we take some fn t defined by say cos 2n pi t comma sin 2n pi t for n say integer, say first of all say natural number, then we will get a different path. None of them are homotopic to each other. Okay. For an example, if you take here 6 pi t comma sine 6 pi t, then also we get it will rotate thrice, and similarly 4 times 5 times in this way. Not even that, not even natural number, even here you can put -1 as well. You can put n equal to -1 as well. That's mean cos 2n pi t comma minus sine 2n pi t. You can choose natural z as well. So therefore, instead of taking this, we can take here in belongs to z. Okay. So that's mean for each values of z, see, if you put 0, then you get that identity 1. So that's mean that only 1 0, that constant path. If you put 1, then we get f. If you put 2, then you will get g. If you put -1, you will get some reverse of f. That is f bar. You will get that one. Okay, so that's mean actually these are forms a group, because if you compose f and f, then you will get g. See, you can verify that. If you take f dot f, you will get g. See, right? You will get g. So in this way, actually, you can say this say if this forms a group, So therefore we prove that pi1 S1 and that point x0, that is isomorphic to Z, and this is the map actually. So this is the map that cos 2n pi t comma sine 2n pi t that goes to actually n. So this is the map. Now idea is very simple. That's mean whenever we are talking about a fundamental group of S1, so that's mean what is my 1, actually 1 means it is rotate 1. Now what is minus 1? Minus 1 means it is going to this direction. So here starting from here go this. This is minus 1. And 2 means rotate to this side. Minus 2 means rotate in the reverse direction. So in this way we can get 1, minus 1, 0, everything. Now note that what is the definition of path actually. So definition of path means any continuous function from I to x. And loop means only the extra condition f0 equal to f1. That's all. You can write it is 0, 1. So that's all. There is no other extra condition. That's mean when you are writing f equal to this one, this is just a path. There are uncountably many number of paths, right? But this is just one path. So there may be any other path. But here interesting fact is that whenever choose any other path, right, which rotate only one times, then by that phi, which now someone said, na, by using that representation, rearranging that domain, you can define that f compose phi. So f compose phi, this one is path homotopic to f, right? So if you rotate only one, whatever the way, it you can always get that this is homotopic to f. So all of these are path homotopic to f, right? So that's mean what I'm saying actually. It may happen that suppose you have a circle, this one, it can be like that. So see my cursor. Now it start from here. It is going to this direction, and suppose it changes his mind. Now it's going reverse back. Then again goes here. Now say again reverse back. Again goes here. Suppose here again reverse back to now stop here. So that's mean ultimately it just takes only one round path. Only goes from start from here and in here. It takes only one round, but in various way, right? Now in that case, you can define one phi such that f compose phi will be that your only this, say this was the g, that g compose phi will be this f. So therefore f, and that will be homotopic to g. So in this way actually we prove that. So proof is not simple at all. So just mentally prepared. So this is the one of the difficult proof in the algebraic topology. So there will be around 4 or 5 different proofs. So one is this fundamental group, another one is Van Kampen theorem, another one is Meyer-Vittori sequence. So these three, which I can say, are the difficult part. So in the next lecture, we will prove that. Now that is very difficult. So just be mentally prepared. Or if you want, you can read also that fundamental group of circle. Now if you read also, then also you will maybe it will be maybe easier for you. Okay. So I stop here.